Hi, everybody. Welcome to the first week of class. I just want to take a few minutes to hit on the format of the class before we get into any content. So, number one, make sure that you take a few minutes to look over the course syllabus. A couple things to note are that I won't be able to give credit for late assignments, but if you coordinate in advance, I'll be pretty understanding. And there's obviously extenuating circumstances, especially if there's any medical issues that result in late work. I'll be sure to work with you on that. Make sure that you obtain the course textbook by Ragsdale. It's a good book. I actually used it when I was in grad school. It definitely focuses on Excel as the main tool for analysis. There's many tools, but we can definitely learn a lot of the concepts through Excel in this textbook. Also, make sure you download the required software for this class. That includes OpenSolver, Excel, the Gurobi package, and the RStudio environment. In the first week, you'll have to make your class introduction, and I'm really looking forward to seeing everybody's personal introduction. Also, take a minute to look in the People's tab in Canvas. I've made critical thinking groups and put every student into a critical thinking group. If you have any special requests, you want to work with somebody maybe you've known professionally or from another class, I can definitely work with you and try to get you into a different group. Otherwise, just get to know everyone in your group and be helpful in the homeworks and reach out to your group if you need anything. And of course, you'll be working together on the project. Also, for this class, there's a few things that we'll be doing same every week. That includes a reading that's listed on the syllabus and in the module. In the Canvas page for each week, there's also lecture notes and supplemental videos to dig into certain skills. There's a discussion due every week. You'll have to make two posts each week. One is due on Wednesday, and another one due at the end of the week, which will be a response to another student's post. There's a self-assessment where it will be graded by a computer, and you'll have two attempts to get the best score you can. And there's also a homework which will be graded, and I'll review those as well. So definitely do your best to participate, reach out, post on the forums, and work with your classmates and myself. Try to get the most you can out of this class, and we can kind of dig into the content now. For the rest of this lecture, I'm not going to hit on every single slide in the slide deck. I think that sort of defeats the purpose of the asynchronous format, but I do want to hit on some of the important topics from the textbook and the slideshow that I think will help you in the homework and your overall comprehension in the class. Make sure you take the time to review the learning objectives every week just so you can get the most out of the modules before you dive into the material. Remember that this week we'll have the reading for Chapter 1 of the Ragsdale book. Make sure you go through the lecture notes and the supplemental videos as you need them. And we'll have one discussion topic which will require a post and a response, the self-assessment, and homework 1. Informs is a large professional society that includes members interested in management science and operations research. I'm a member. Here's one of my Informs textbooks that I reference all the time. And people in Informs came to the definition that analytics is the scientific process of transforming data into insight for better decisions. I like that definition, but there's others. My doctoral advisor defines analytics as discovery and translation of data-driven actionable insight into effective decisions using mathematics, statistics, engineering, economics, and computational science. One of the most fascinating aspects of operations research to me is that there are a variety of tools in our toolbox. Some of those include our optimization methods, of which there are many, simulation methods, an innumerable number of simulations out there being used today, and decision science tools to develop decision support models and make better decisions. The textbook's rich with case studies and other examples with organizations employing ops research to meet their goals. A lot of those are in business. We have Procter & Gamble lowering their inventory and reducing cost, and that produced a return on investment of $1.5 billion for their company. It's not just business problems, though. I've seen it in political campaigns trying to maximize the reach of their advertising materials. The Department of Defense uses analytics to optimize their spending of weapons and communications equipment. I always like the example of the farmer at a kibbutz trying to optimize his portfolio of carrots, potatoes, and corn based on the constraints of the amount of money he can spend on seeds, the amount of water he has, and the amount of labor he has or she. So these are just some of the ways that people do use operations research in practice to solve their problems. Please make sure you spend a little bit of time to look at the definitions of the types of analytics. The book has some nice discussion. With an increasing level of rigor, we consider descriptive analytics that look at what has happened in our data, diagnostics to ask why did that happen, predictive analytics get into based on what we know now, what can we expect in the future, and finally, prescriptive analytics answer the question, what should we do to reach our goals? Since we are spending the whole semester on operations research and many of you will continue to work in the field, I thought it'd be important to talk about the origins of the field. It came about in World War II as the Allied powers found that they were very resource constrained and had a lot of strategic goals and needed a little bit of direction to get to those goals. Some of the problems that they started solving were submarine placement in the Atlantic, and they also used operations research to optimally locate the radar stations in the chain home station that were part of the Battle of Britain. And some of the results were very promising. The military powers kept investing more and more into operations research. And after World War II, it became a widely growing field in the civilian sector, largely for business and engineering purposes. There's a couple slides covering the nature of operations research, and this is pretty interesting to me. Operations research is always a team effort. We're always providing analysis for some decision maker, whether it's yourself or an executive or some other customer outside of your organization. When we do operations research in the field, it usually involves a team effort with players like subject matter experts, data scientists, and decision makers sitting alongside the operations research analyst. Optimization is a huge topic in operations research. It's not the only topic, but it's one area we spend a lot of time in it. It's constantly evolving. People are inventing new algorithms and new ways to solve really complicated problems better than they were able to solve it in the past. We'll define optimization as finding the best decision according to some criterion in a quantitative way based on your constraints. Another big camp in the operations research field is simulation. Simulation is usually used to better understand a complex system where you have some assumptions and some unknowns in the long-term behavior. Usually there's some sort of time element incorporated into simulations, and you can run the simulation many, many times over and over again to find the best case results, the worst case results, and you change the input parameters and you find these edge scenarios that can help you learn about your system. I've seen pretty interesting simulations for the stock market. I've seen simulations for how aircraft interact with each other in combat. And another cool simulation just for fun is the Sims game series, where people will line up and behave in funny ways based on human nature. And you wind up with an amusement park with long lines and all these unexpected results because, well, you don't know what's going to happen until you run the simulation. Another interesting aspect is there is a way to use optimization and simulation together to make some really interesting insights. After you've ran the sim and you have enough data points to understand their nature, you could use optimization to make best decisions for when you go into the real world and you're deploying your system. To fit in the classical definition of operations research, we do require that there's a mathematical model. Just keep in mind that there's a lot of different ways to model these things, and some forms of your model are better than others. Part of the art of operations research is deciding the right tool for the right problem. And there is data. Always try to find the best data you can for the right problem, and that does take some experience. This is where we need to start to play the part of a data scientist, or at least have a data scientist on our team. These tasks include data preparation, data imputation from missing data, dimensional reduction, or feature selection and feature engineering, just to name a few. Speaking of math, part of our content this week is reviewing some of the math that you've hopefully seen in previous courses, either undergrad or graduate level. Take a minute to review the common mathematical operators that you see here. I also want to take a minute to define what is a mathematical model. A model is an abstraction of a real world problem, somewhat like artwork, and it needs to be detailed enough to capture the true essence of your system, but not have too much detail that there's going to be inaccuracies. Also, be simple enough that it's computational attractable and understandable to a human analyst and the decision maker. Maybe you haven't thought about it until now, but I promise you, you use models every day. Some of these include mental models, even things like, let's say you're walking down the street and you're watching a car, you can project in your head the next action of that car, and that's a mental model. Visual models are things like maps when you use your GPS to navigate around a city street. Physical models include these clay models of a car that they show in advertisements as they're developing the real thing. Sometimes you'll have a dollhouse to represent a real physical building structure. And then mathematical models are really a core competency in operations research. And this is where we could really start to get some insight into the most complicated systems. Hopefully you've seen regression before, and hopefully fairly recently. If you've forgotten or you've never seen it before, either send me an email to talk about it or hop on YouTube for a refresher. But regression is an optimization problem, and Ragsdale classifies it as a predictive analytics. I think regression could probably play a role in descriptive, predictive, and prescriptive, but that's besides the point. Regression is also one of the reasons why we have to review our matrix mathematics in this class. Hopefully it's also a review, but we'll get to that later in the lecture. If you haven't seen it before, I'd like to orient you with the standard form of an optimization problem. On the screen we have a linear optimization problem. This one's to maximize something with a utility vector C. If it's minimization, we might call it a cost vector, and a decision variable x. That's actually a vector as well. So when you multiply with vector multiplication C times x, that's the total cost or the total utility of the solutions you've selected. There's also constraints in our optimization problems. Those are stored in a matrix A, and with matrix multiplication, we say AX is less than or equal to some vector B. And we'll learn how to formulate these problems that CX matches your true system and AX less than B matches your system. And finally, in this problem, we show that all of our decision variables have to be greater than 0. And that's realistic for a lot of problems, especially if you're trying to allocate the number of dollars to something, because it might not be reasonable to have negative dollars or negative water or negative quantity of people for a lot of types of problems. If you need it, please take a little bit of time to review your linear algebra, including vector and matrix operations and definitions like linear independence, Euclidean space, determinant, inverse, and rank. The definition of matrix non-singularity is a big concept in operations research and data analytics. If a matrix has a determinant that is not equal to 0, then it's considered non-singular. That allows you to take the inverse of the matrix, and that gives you a lot of opportunity to use certain mathematical tools to do regression and data compression and other things that we need to solve these optimization problems. The slides contain a couple different methods to solve the inverse problem, including Cramer's rule and Gauss-Jordan elimination. Make sure you're familiar with the definitions of rank of a matrix. Remember that the row rank of A is the maximum number of linear independent rows of the matrix A. Column rank is the maximum number of linear independent columns of A. Note the following conclusion of linear algebra: if you let A be an n by n matrix, and you claim that A is invertible, then you can also say that the rows of A are linear independent, and you could also say the columns of A are linear independent. The rank of A equals n, and the determinant is non-zero. We can further use a series of elementary row operations to transform A into the identity matrix In. When we augment the matrix A with the solution vector B, we call it the augmented matrix. And note that it's only possible to find a unique solution for your system of equations when the rank of A equals the rank of A augmented B equals n. That's called a consistent system. Convexity theory is the final topic that we're going to cover in this lecture. Make sure you do go through and understand all these definitions, including requirement space, convex, concave functions, and polyhedral sets. I'm just going to go into detail on a couple. This one is easier to understand when you have a visualization. So look at this function. You have a line segment. You have a set y such that y equals alpha x1 plus 1 minus alpha times x2, where alpha is a scalar between 0 and 1. What that is, it's a convex combination between these 2 points so that no matter what alpha is, when you evaluate that function, you're on one of these points. And that convex combination is a concept we're going to build on. Now think about a convex set in the broader sense. Besides just our convex combination on a line segment, we might have a more interesting set. On the left, there's a polyhedral, and if you pick any x1 and any x2 in that polyhedral, you'll be able to satisfy the requirements of our convex set. Whereas on the right, we pick point x1 and point x2 in that donut-shaped set, and there exists sudden alpha where if you evaluate your point, you're no longer in that set, somewhere here in the middle, and therefore the right hand side donut shape is not a convex set. Read the definition of an extreme point. A point X is an extreme point of S if X cannot be represented as a strict convex combination of any other 2 points in S. So if you look in the shape on the left here, there's a convex combination in red between points x1 and x2. And there's a point in the middle, just represented with a dot. We know that that's not an extreme point because it's been represented with some alpha as a linear combination between x1 and x2. But if you look on this set on the right, there's an extreme point, and there's no convex combination of other points that you can come up with to set alpha such that EP is in the convex combination. Extreme points have a very special meaning in linear optimization. Consider the polygon on the left. If you look at this extreme point, you know it's an extreme point because there's no convex combination of any other 2 points that still contain your extreme point. And now you imagine that this is the feasible region for some linear optimization problem where the gradient goes up, meaning the higher you get on the page, the better your solution becomes. So if you keep traveling up in that direction, eventually the highest point you can be at is that extreme point. And this concept keeps coming up in linear optimization, as we'll learn later in the semester, that the extreme point of a linear solution space tends to always be your optimal point. Now that we've built the intuition for a convex combination in a convex set, I'd like you to read the definition of a convex function. Given a convex set S in space E with f of x defined for all x in S, f is convex in S if this function, remember alpha is a scalar, and you have points x1 and x2, satisfies this inequality where you rearrange the variables for alpha, x1, 1 minus alpha, and f of x2. So try to take a minute and think what the heck is actually happening in this inequality. Well, let's break it down. On the left-hand side, we're evaluating this function. Think about a set x1, set x2, shown on this graph, and think about the convex combinations happening inside that function, resulting in some output. So the output, as we change alpha, are all these points along the curve as we evaluate different alphas and some values between x1 and x2 as alpha goes to 1. Now think about the right-hand side of this inequality. The convex combination is applied to the outputs of the function. So that's a bit similar to what we've seen in the past with convex combinations, where there's a line segment drawn between the 2 points, f of x1 and f of x2. Naturally, now you're going to ask yourself why all of this even matters. Recall back to this definition that x1 and x2 have to exist and be defined everywhere inside set S. So if we're considering any x1 and any x2 in set S, and we're able to satisfy this inequality, then that function is convex everywhere inside S, the set S. On the other hand, sometimes we have functions that are convex only locally. So maybe we can create those convex combinations and meet that inequality to be true only in this region of this function, but it would not satisfy the inequality in another region. And that's what we call locally convex or convex within some domain. Overall, this function that we're seeing here is neither convex nor concave because we can't satisfy the definitions of convex nor concave for the whole function. Optimizing convex functions tends to be a much cleaner task than optimizing non-convex functions. When it's convex, we can use a greater variety of algorithms that solve the optimization problems more efficiently, so in less time with less computational resources, and typically more accurately than optimizing the non-convex problems with the more general solver algorithms. In the early days of machine learning, when people were still getting used to the idea of a simple neural network, there was a lot of debate, theoretical debate among experts that said, is the problem of optimizing the weights to a loss function on a neural network, is that a convex problem or a non-convex problem? And over time, the consensus became that the loss function on a neural network is non-convex, and that influenced the types of solvers that researchers and practitioners use to fit the weights of a neural network. Today, everyone thinks that they're non-convex, and the solvers have become quite complicated on these really large neural networks. And a typical algorithm that we use in the convex domain just wouldn't work in the world of neural networks anymore. So with that parting thought, thanks for listening. Please take the time to review the rest of the slides that I didn't go into in depth. Make sure you complete all of our tasks for this week, including the introduction discussion post, the modules discussion post and response, the self-assessment, and the homework. I'd love to hear some feedback on this video. These videos weren't part of the course in previous semesters, but I thought I would try to provide at least something for a little bit of a touch point with students. So send me a note or leave a comment if you have any thoughts on how it could better help you in the future weeks. And other than that, good luck on your self-assessment and homework.